Okay, welcome to the 23rd Reading Online Sports Economics Seminar. Today, at the leisurely afternoon time of 2:30 p.m. in the UK, 3:30 in continental Europe, we have Scott Kaplan from UC Berkeley over in California up at 6:30 in the morning. We're delighted that he's been willing to get up so early in the morning. He says he'd only do it for a sports economics seminar, so we're really pleased that we are a sports economics seminar and that therefore we can be privileged to have Scott's job market presentation of his job market paper, Entertainment Utility from Non-Instrumental Information, Evidence from Consumer Attention. As always, please keep your microphones on mute. Please also switch off your cameras as well, just in case there are weaker internet connections. Feel free to ask questions in the chat feature if you can access it. If you can't, you can either hold back until the Q&A session at the end, or you can send me an email with questions that you have. Scott will talk for about an hour. He's got about an hour to talk in, and then we've got time for half an hour of Q&A. Without any further ado, Scott, please do take away your talk.
Thanks a lot. Yeah, thanks for having me. I'm going to go ahead and try to share my screen here. Let's see. All right. Can everyone see this okay?
Yep.
And still okay?
Yep.
Alrighty, cool. Well, yeah, thanks again, James, for the introduction, and thanks for having me. One of the nice things I was saying on Twitter yesterday, one of the nice things about the virtual environment, although there are so many not so nice things, is the ability to present in a faraway place from your own home. So it's exciting to be able to be here at 6:30 and talk about some sports economics with the group. I think that will have some really good feedback for me. So the title of this paper has changed a little bit. It's called Entertainment Utility from Suspense, Surprise, and Star Power. And this, as James mentioned, is my job market work. A little bit about me: I'm a sixth-year PhD candidate in the Department of Agricultural and Resource Economics at UC Berkeley. My research is primarily focused on applied micro empirics and theory, looking at it through the lens of the consumer, and taking a more IO methods approach, as well as a reduced form causal inference econometric approach. Okay, so without further ado, let me jump into the motivation for the paper. So I want to tell a story to motivate that's a story about information. And as economists, we are familiar with the idea and the notion that information helps agents make welfare improving decisions. But there are actually two distinct classes of information that I don't think get talked about all that much. In the first class, which is called instrumental information, is probably the class of information we're mostly familiar with, where this is information that acts as a direct input for decisions when contingent actions are required. So if you have information about, I've done some work on the Berkeley soda tax that we put into place here. If you have information about a tax going into place, that's likely to change, or should, in theory, change your habits or consumption patterns regarding soda. So there's sort of a contingent action that follows the information provision of the tax itself. And there's a lot of work that's done, of course, in this field, both on the theoretical and empirical sides. There's an entirely sort of different class of information that I think is less studied, but I think is quite important, especially from an economic standpoint, and that's called non-instrumental information. So this is information for the sake of attention and attention capture and entertainment. And so going forward, I'm going to refer to this type of information as thrill. And so those of you here that are sort of in the sports world, I think sort of already see where that thrill component is going. But non-instrumental information is basically information that doesn't come with the following set of contingent actions. So if I'm refreshing the New York Times or my social media feed, or mostly recreating or consuming entertainment, there's not necessarily contingent actions that result from that information that's being provided to me, but it still provides me utility nonetheless. And I'm going to break down these primary characteristics of thrill into two more specific characteristics that are more applicable to the entertainment and sports spaces. And so suspense, I'm going to call, is a higher suspense event or moment is when there is higher variance in future beliefs over an outcome. And I'm just going to give the intuitive definitions here. We'll really jump into a more formal visual, and if you're interested, mathematical definition of both suspense and surprise. But this is just meant to get us off the ground. Surprise is when current beliefs or realized outcomes are further from beliefs in a previous period. So to sort of summarize, suspense is a forward-looking metric where at any given moment in time, we have a higher suspense moment if there is higher variance in our future beliefs over some outcome. In sports, that's going to be the final outcome of a game. Surprise, again, is a backward-looking belief, and we have more surprise when our current belief state is further away from our beliefs that existed in a previous period. I'm also going to talk about and think about the quality of agents conveying the information, right? So, you know, James and I playing in a tennis match, I don't know how good James is, but if he's as good as me, then he's not that good. And that could be a very suspenseful or surprising match based on these definitions here, but certainly the skill or the quality of the agents conveying that suspense and surprise is not all that impressive. So I want to introduce the notion that the quality of agents conveying information may infect demand in this case. In this case, this is going to be sort of in the sports setting, going to be superstar players. And finally, to motivate this from sort of a zoomed out standpoint about the value of this project, the global entertainment media market is approximately valued at $2.2 trillion. But I think even more importantly, it's grown 60% in the last 10 years, and I think is going to even continue to grow as incomes rise around the world and people have more disposable income to consume on recreation and entertainment. Another sort of interesting finding comes from the Aguiar et al. 2011 AER study that says 20% of waking hours of individuals they spend consuming entertainment, which is certainly not a negligible amount of time. So the primary research question for this study is, how does the skill, which I'll also refer to as star power, of performers, and thrill, which again I'll refer to more specifically as suspense and surprise, affect spectator demand for entertainment? And this is going to be a very empirically heavy approach to answering this question, founded by a little bit of applied micro theory about the consumer. And so some more specific questions that I'm aiming to answer with this work. First, my goal is to try to convince you through some interesting identification and rigorous empirics and rich data that consumers are willing to pay quite a bit to experience star power. So that's the first question I'll set out to answer here. Then I want to turn my attention to a slightly different setting. So to measure that willingness to pay to experience star power, I'm going to rely on ticket marketplace data. And then I'm going to shift to TV viewership data and think about a twofold sort of question there. First, do skill and expected thrill increase initial viewership of an event? So I'm going to be thinking about how the initial decision of a spectator to tune in to a sporting event is affected by the skill that's present in that event, or the star power, as well as the expected thrill that's going to take place during that event. And I'll elaborate more on what I mean by expected thrill there. Then the final sort of stage of that threefold analysis is going to be, how do spectators respond to skill and thrill during an event? And so I'm actually going to use within event variation in both suspense, surprise, and star power to think about how viewership responds to each of them, as well as some interactions between them. Which gets to the third question: is there an interactive effect between skill and thrill on viewership? So this is the idea that when there's changes in thrill, do viewership responses differ depending on how much skill is on the court at that time? And so I'll talk more about that at the end. And finally, which I won't speak about in this presentation, but I think is important to mention nonetheless, and certainly on my radar as I continue this job market work, is, are there counterfactual entertainment structures that increase viewership using empirical estimates of responses to skill and thrill? I have a couple interesting ones in mind, which maybe we can dive into a little bit during the Q&A, but I think that's a cool and interesting avenue to explore given the estimates that I'll present here. Okay, so the research, the empirical setting for the research is the National Basketball Association. So just to overview what kinds of data I have and why I think it's a useful setting to look at this, I have data from the 2017-18 and 2018-19 seasons. I have the NBA is valued at $8 billion annually in terms of their annual revenue, and actually I think it's the highest growing professional sport. It may have changed recently, but from the research I've done, it's the highest growing professional sport at 4% annual growth. And so that's, I think, an interesting motivator that this is an important and fun setting that spectators value quite a bit. What's nice about the NBA is there's a pretty convex distribution of player popularity. So it's very, I think, similar to European soccer, where you have a lot of weight in terms of the popular players placed on that top handful of superstar talent, instead of a league that has a more even distribution of player popularity. The NBA certainly has a lot of weight placed on those players right at the top of the distribution, and it's also observable. So I observe essentially observable metrics of the player's popularity, which I'm going to be using number of fan all-star votes for each player, which I'll elaborate on in a bit. A characteristic of basketball is that there's high frequency of scoring, which provides smooth updating and thrill. This is certainly going to differ from a sport like soccer or even football, where scoring is much more sort of spiky, and that's going to have implications for how thrill is calculated and is understood in this setting. So just an important thing to mention. What's great about the NBA, and maybe you can tell me otherwise, but there's really great access to rich play-by-play data, as well as ticket marketplace and TV viewership data, which I think is quite unique to the sport. I think I've seen some really good studies looking at soccer data, but in terms of US sports, the NBA has a really nice platform to access their play-by-play data, which pairs nicely with ticket marketplace and TV viewership data that can be matched. And finally, a more structural part of this league is that there are locally televised and nationally televised games. And what's, I think, nice for this setting is I'm going to be looking at only national TV games from my TV viewership data, and national TV games don't overlap. And so there's, or primarily don't overlap. There's a couple of situations where they might overlap briefly if one game runs long, or if there's, sometimes there's playoff games, not this season, but sometimes there are playoff games that tend to overlap depending on if there's 2 or 3 per night. But generally they don't overlap, and there's little substitution then towards extremely similar programming while a national TV game is going on. To preview the findings, 3 sort of primary findings I think to preview as I go into the more details of the analysis. First, in terms of the willingness to pay for star power, I find that spectators express significant demand for popular players. And so my identification strategy basically relies on exogenous announcements of players missing games and how ticket prices on a secondary market are responding in a pretty high granularity way in terms of I observe them at 30-minute snapshots. And so I find that ticket prices fall 4 to 16%, which amounts to about $7 to $42 per ticket for games in which the most popular stars are absent. And I find that there's also interesting heterogeneity in home versus away game absences, which I think is intuitive, given that the structure of the NBA schedule is a player or a team plays 41 games at home, but only at most 2 games on the road during the regular season. And that scarcity effect certainly pops up for some of the top players like LeBron James and Steph Curry. Second is I find that the range of thrill produced by an event is massive. And this is going to tie into how I'm defining a thrill, which is taking from some seminal work by Ellie et al. In 2015 from the JPE, where they define suspense and surprise mathematically. So using their definitions, I find that a 0 to 2 point game in the fourth quarter averages 18 times more suspense and 14 times more surprise than a 14+ point game. To give it some sort of context on the range, it's not all that uncommon to find different, to watch games that are 0 to 2 points in the fourth quarter versus that are 14+. So this variation is observed quite a bit. Finally, I find that TV viewership is highly responsive to thrill. So I find that there's approximately a 15.8 to 29.6% viewership increase for games that experience this 14 to 18 times more thrill. And there's several different approaches I use to get at that range, and I'll talk about that in a little bit. Interestingly, I also find a negative interactive effect between suspense and star power. And so essentially when a game features increases in thrill, the viewership response is heightened when that game doesn't feature as much star power. So this is to suggest that games featuring lots of star power typically have a more constant viewership path, whereas games featuring less star power tend to have a much more viewership tune-in mechanism, basically, to when a game gets more thrilling because people weren't watching that game before because there wasn't very much star power. Quickly, just to overview some of the related literature and where I think this work fits in, and some of my contributions. I won't belabor this slide too much, but I will point out for this audience that there's a lot of really great work about outcome uncertainty and TV viewership in sports already. And I think this work complements and builds nicely on that. First, there's a small but obviously super relevant literature on suspense and surprise. And so again, I'll be taking definitions of suspense and surprise from that Elliott et al. Paper and modifying them slightly to fit my setting. But there's been a couple of other notable, I would say, empirical studies already looking at suspense and surprise. This Bizzozero et al. 2016 paper is looking at, tennis matches and how suspense and surprise are evolving during the course of a match. The Baraimo et al. Study, as recently published in 2020, is looking at suspense and surprise, and they introduce another factor called shock and look at European soccer. So I think this study, again, complements those nicely by introducing the star power element, as well as looking at a completely different sport and geographic setting. The second body of literature is on information preferences and outcome resolution. So this literature is highly, work a lot by Gary Becker. And this is where a lot of the outcome uncertainty work that's been done in the sports domain. I know some of you are here that are on this list. And yeah, it's been really fun to read those studies and see how they complement my own work. The third body of literature is on hedonic value and hedonic pricing. And that was begun by Sherwin-Rosen in his seminal paper in 1974. I think this literature is especially relevant to this study because Sherwin-Rosen also has the seminal theory of superstars. And so thinking about how superstar athletes and players provide value to events and how those effects may or may not look, I think was started with him and continued through some other great work. Hausman and Leonard looks at how TV ratings respond to superstar presence during the Michael Jordan era, which I think is, again, a nice complement to the type of work I'm trying to do here. Finally, I think there's a nice, large, and rich literature on consumer attention and advertising. So this is more in the marketing domain. And there's been some good work here that I think certainly applies to this setting where I'm essentially measuring consumer attention to things that either potentially keep the attention, if there's more thrill or more star power versus don't. And so my contributions, I think, in this study are threefold. I develop a holistic model of spectator utility from entertainment. I developed novel measurement of demand for important product attributes in entertainment. And it's the first empirical analysis, to my knowledge, that jointly assesses skill and thrill in the same study. So I'm just going to keep an eye on time here. Just a quick outline of where we're going with this. I think a visual outline is appropriate because there's sort of several different dimensions of the study that I think are important to note. I want to approach this work from the lens of the spectator. So I'm going to start with a spectator model of utility framework in my head and present that in a little bit. And I'm going to take two data-driven paths to look at this, this sort of analysis. First, I'm going to be looking at secondary ticket marketplace data and using that variation in that data to assess willingness to pay for skill or star power. And then I'm going to turn to the TV viewership data where I'll both look at initial viewership, tune in to skill and expected thrill, and then within game viewership adjustments in response to thrill that evolves during the course of the game. And in that within game viewership analysis, I'm actually going to use a more observable metric of thrill, which is deviating slightly away from the Elliott et al. Structural definitions of suspense and surprise. And then I'll apply the Elliott et al. Definitions more directly. And in that model, I'll be interacting both skill and thrill together to think about some of the joint effects of the two. Okay, so starting with the ticket price data and estimating willingness to pay for star power. So just to quickly overview the data I'll be using here. 3 sets of data that are important for this analysis. The first is game characteristics data. So this provides me fixed information about each game and player. Again, the measure of skill I'll be using in this study primarily. And of course, there are other logical measures to use, but I think this is a nice one because it's extremely observable and it involves the popularity element of the players. Is the number of fan all-star votes for each player. So each year the NBA has an all-star game. They allow fans to vote on which players they would like to see as starters in that all-star game. And so I observe essentially how many all-star votes each player receives, and I'm going to be using that as my continuous measure of skill. In this analysis, I'll be looking at specific players, specific superstar players. And so the selection criteria for players was that they were an all-star starter during either or both the 2017-18 and 2018-19 seasons. This is a nice pairing with my measure of skill because players that are selected as all-star starters, 50% of the weight to that selection is from the fan all-star vote metric. And so that's the highest weight placed on that selection criteria. And then I'll have team information, location, date and time of the game, etc. That it's going to be important in matching announcements to ticket listing level data. And so the second set of data is player absence announcements from Roto World, which is a really popular fantasy sports website. I have the date and time of all absence announcements for these selected all-star players. And I can match that again with the secondary ticket marketplace data, which I get from a large online marketplace. This data is really cool because it provides, I have 30-minute snapshots of all listings for all regular season games, which amounts to close to 2,500 total games over 2 seasons, beginning 3 days before each game. And I'll sort of show you the distribution of announcements and why that 3-day window is a pretty good window for capturing some of these effects I'm setting out to measure. So some quick summary statistics about this data. This graph shows 3 different trajectories by hours to game, which is mapped here on the x-axis. And so the first pane is the number of active tickets on average per game on the marketplace by hours to game. So you can see that it's pretty constant around 300. And as you get to about 10 hours before a game, it starts to drop off because the number of tickets that are added, which is in the second pane, is totally dominated by the number of tickets that are sold as you get closer to a game. And there's some really nice work by Andrew Sweeting, 2012 in the JPE, that looks at basically game theoretic dynamics between buyers and sellers on these marketplaces and explains a little bit as to why you have this pattern of more constant tickets added before a game versus a really heavy amount of tickets that are sold or occur right before a game, which leads to this type of average price trajectory by hours to game. So the y-axis here is the average price of a single ticket for an NBA game during these seasons. The x-axis again is hours to game, and you can see that the average ticket price hovers between 140 and 150 up until right about 10 hours before a game, where it takes a nosedive on average. That period also is associated with lots of price volatility, but on average, the ticket price falls quite a bit, which is a result of some of the quantity dynamics I showed on the last slide. Finally, I wanted to show a histogram of the distribution of player absence announcements by hours to game. And so the y-axis here is measuring the count of absence announcements by hours to game here on the x-axis. And what you can see is that most of the announcements for these NBA games, or these exogenous single game announcements, occur within the 10 hours before a game. So basically the day of a game, which can start in the morning, all the way up until just before game time. You see a lot of announcements also occurring the day before a game. So if the way the typical NBA schedule works is games are often separated by an off day. So during that off day, you'll sometimes get absence announcements about players that are going to miss the game on the following day. You have a logical dip in announcements here and sort of between these 2 periods, because that's basically the nighttime hours of the US when people are sleeping. But you can see that the number of announcements sort of drops off precipitously as you sort of move past that 1 day before time window. Okay, so how am I going to empirically measure willingness to pay for star power? 2 different approaches that basically both rely on this difference in differences analysis. So I'm going to be regressing price at the listing level for game J, the listing found in section H, S, and at hours to game H. And regressing that on absence, which is an indicator variable for a treated game, so equal to 1 for a game that's treated by a superstar absence announcement. Post announcement, which is the post period of when the announcement takes place in terms of hours to game, and then the interaction of the 2, which gives me the coefficient I'm interested in, which is beta 3. And again, the 2 differences here are treated versus untreated game, which is defined by a treated game being a superstar player is announced out, and I have that announcement in front of me and available to me, versus an untreated game where a player is not announced out, where any superstar player is not announced out on a team. The counterfactual I'm going to use here for this analysis includes games for a specific player's team that don't feature other superstar absences, right? So for example, if Stephen Curry misses 7 games during the 2017-18 season, I would have 7 treated games, but I wouldn't use the remaining 75 games as my control games, because some of those games are going to be conflated or confounded by another superstar's absence, whether it's Kevin Durant or or superstar on the opposing team. So that set of counterfactual games depends heavily on the fact that there's no other superstar announcements for that game. I'm going to then expand on this differences and differences approach to do a more continuous version of it, basically to measure the ticket price effects in really high granularity time intervals before and after the announcement. So as I mentioned, my data is at the 30-minute snapshot level. And so I look at 14 30-minute periods before the announcement and 14 30-minute periods after an announcement. So that amounts to 7 hours before and 7 hours after. Absence here is a vector of interactions between a treated game and the event time surrounding when the announcement takes place. And D sub T here is a vector of coefficients that tells me the effect of the absence on treated versus control games, again, pre versus post announcement. And again, the nice thing about this data is that I'm able to have these game by section level fixed effects. So I have like section 201 for this game on this day that is controlled for in terms of their average effects. And then I also have a general hours to game fixed effect indicator or trend that, not trend, sorry. It's an hours to game fixed effect that it controls for each specific 30-minute interval before a game. And this sort of second component is necessary for confirming parallel pre-trends and prices. And that's important for getting at a causal estimate here. And so to sort of overview the results of this work, I sort the players here by their differences impact on ticket prices. So the x-axis here represents the diff estimator for price levels. So LeBron here has an average price reduction associated with his absence compared to games where he's not absent of $42 per ticket. Steph Curry is second highest, and sort of you go down the list and you start to get some players that are insignificant down here. I was surprised to find that Giannis was basically a null effect, given that he was the league MVP last year. But you see, interestingly, that some of the popular players that are maybe a little bit less skilled during these seasons, like Dwayne Wade and Dirk Nowitzki, have really high effects, likely due to this sort of career legacy popularity effect here. There's some interesting, maybe I'll show really quickly, home versus away results. You can see that LeBron and Steph Curry totally dominate the away game effect. So when LeBron misses an away game, there's a price reduction on average of $75 per ticket. And when Curry misses an away game, it's about $55 per ticket. So the most popular stars you can see here are the ones that are generating the biggest scarcity rents in these away markets. Some other players have interesting, like for example, Luka Doncic has a much larger home effect than away effect. We can hypothesize about why this might be. He's obviously a very important component to his team and has a ton of competitive value for helping them win. So these results I find are pretty interesting too. So I map these differences effects by the number of all-star votes for these players. So I can basically get a more continuous relationship between the skill metric that I'm using, which again is the number of fan all-star votes, and the diff impact these players' absences have on tickets. And what you see here is there's a pretty noticeable convex relationship between skill and their diff impact. And so this is actually in line with the theory presented by Sherwin Rosen in his 1981 work on the theory of superstars, that there's this convex returns component to superstars, which you observe here, that there's convexity in people's willingness to pay for star power. Finally, just an example of one of the event studies for the players. This is the event study for LeBron James. What you would want to see here, which is what you do, is that the effects prior to an announcement and event time are insignificant from zero in terms of the treated game versus the control game. Once an announcement takes place in event time, the prices for the treated game fall in line with as time sort of goes past the announcement. So there's not an immediate drop associated with an announcement, and that's because there's obvious frictions on in information. Basically, people aren't directly observing the announcement and then going right to change their ticket prices. They may see the announcement a couple hours or a few hours after it's released, and then decide to adjust prices as well. And if people are interested in the other event studies, we can talk about those during the Q&A session. Okay, so now I want to sort of pivot a little bit to talking about the model of entertainment utility overall. And To do this, I want to first provide some visual definitions of thrill. So Ellie et al. Has a really nice and rigorous mathematical framework to define thrill, but I want to sort of step back a little bit and use the empirical setting to motivate the definitions here. And so this graph is an example game, that playoff game that occurred on April 13th, 2019. And this is just a graph of how the real-time win probability evolved during the course of the game, right? I have real-time win probability data at the second by second of play level, which is again a great feature of the NBA play-by-play data. And you can see here that in the beginning, Denver was supposed to, or their outcome probability was higher than 50. They were favored to win at that point, and then the Spurs sort of took over. And there are some spikes here towards Denver, but in general, the Spurs maintain control and end up winning at the end of the game. So I want to use this example to motivate the definitions of suspense and surprise. And so if we find ourselves, let's say, just after halftime, and we don't know exactly what's going to happen to the outcome probability during the rest of the course of the game, we would find ourselves in a low suspense situation if the variance in future outcome probabilities in terms of how they're going to evolve in this designated window of time. This window I provided here is approximately 3 minutes of play time. A low variance in how that outcome probability can evolve would be corresponding to a low suspense situation. Okay. On the other hand, a variance that's quite high in terms of where the outcome probability could go is corresponding to a high suspense situation. And you'll notice here that in this previous slide, I sort of have this first order Markov assumption where on average, the outcome probability basically stays the same as it was at the previous period. This first order Markov process is constant. There's no trend. You can also, of course, define a first order Markov process that does have some sort of mean adjustment trend, which I show here, right? Because when you're getting closer to the end of a game, it makes much more sense to think about a mean adjustment trend because a team has to win by that 48-minute mark, which is the end of an NBA game, and so you expect that the trajectory is going to either it's going to move in a direction that fits that characteristic. Okay, and so in words, again, higher suspense means higher variance in future beliefs over an outcome. In terms of surprise, what we want to think about is how current beliefs are different from previous beliefs. So if you look at towards the beginning of a game, in this, again, about 3 minute window of playtime, it's important to define what window you want to look at suspense and surprise over, because of course that's going to have implications for the different belief structures. In the beginning of a game, you might have a situation that's pretty low surprise where the probability between this further along point and this less further along point are basically identical here. And so that would be characterized as there's very little backward-looking variance in the belief updating structure. There were no spikes in between these 2 points. And so that would be a low surprise situation. On the other hand, if you look at, again, sort of a 3 minute window towards the end of the game here, you can see that the belief or the outcome probability updated quite a bit, right? So it went from pretty close to 50-50 to San Antonio taking a really resounding lead in terms of outcome probability in a very short period of time, again, like about a 3 minute window. So that would be a high surprise setting. And then in words, higher surprise means that current beliefs are further from past beliefs. And I'm happy to jump into the math definitions. They're kind of hairy, but we can certainly talk through them during the Q&A if people are interested. Okay, and so now applying these definitions and my definition of skill, which again is the number of fan all-star votes per game, then I can basically build a comprehensive utility framework that's a linear utility function that includes each of these components. And so let me walk through what each of these components are in this case. Bj is just a baseline level of utility for event J. I allow the individual to gain utility from skill that evolves in a sort of a linear way with the more time you spend watching. So for every minute I spend watching the game, I consume the amount of skill in that game in each of those minutes, and that gives me some marginal utility phi here. I also allow the individual to get utility from thrill, and I want to emphasize that this model is from the position of before a game starts. So I'm a consumer. I'm deciding whether or not to watch a game and how much of it to watch before a game starts, before I have any information about how the game has evolved up to now. And so I have some sort of expectation function of thrill here about how thrill might evolve over the course of that game. And I'm gaining all the utility from that thrill for as much time, little t, as I spend watching the game. So that's why I'm integrating over that expectation function here. And then finally, I allow for an interactive effect between skill and thrill here. So if there is some positive or negative interaction between how heightened skill corresponds with heightened thrill, that would be captured in this term here. The cost function I have for the individual is I have cost of two different components. T is the cost of basically the opportunity cost of time spent watching a game. And V sub j, I think this X sub j should actually be a V sub j here. Sorry about that. V sub j is essentially the cost of all the time invariant event specific costs, which is why I just index it by j. And then finally, I have an individual utility shifter, which is Z sub I. And that's, again, that's allowing for flexibility in how an individual experiences utility from an event. Okay, and so there's two primary decisions a spectator has to make in this setting. First, they have to choose the optimal T star to spend watching an event, and then they have to choose how to allocate T star across a game, right? And the assumption I'm going to rely on for this, which I think, and I'll try to convince you in a little bit, is I think a decent assumption is that the change in expected thrill as time remaining increases is less than 0. And so what that means is expected thrill is monotonically decreasing as you have more time remaining in a game, right? So in other words, as you get closer to the end of a game, the expected thrill, again, from the onset of the game is increasing as you get closer to the end. And this is basically a function of the fact that thrill is heavily dependent on time remaining. The closer an event is to finality, or the closer we are to an outcome being resolved, the more spikes you can essentially observe in the outcome probability, which allows for both more suspense and surprise. So with this idea in mind, basically a consumer who's deciding to allocate time to watching an event from the start of an event should basically allocate time starting from the end of an event, working backwards, right? Again, this is assuming that a consumer is making that decision before they know anything about an event. If they're sort of updating their beliefs as an event goes on, then this decision, of course, could change depending on how the trajectory of the event is playing out. And so the solution to the sort of implicit expression for T star is solved for when the marginal opportunity cost of time is equal to the marginal benefit of skill plus thrill plus the marginal benefit of the interaction between the two. Okay. And so now I'm going to turn into the TV viewership data and think about two different settings, the initial viewership decision and how viewership evolves within a game. And just to provide some quick summary statistics about the data here, I don't need you to pay attention too much to this table. I'll sort of walk you through the important parts. In this data, I have 477 nationally televised games over these 2 NBA seasons, giving me 15-minute interval TV viewership data. There is 1-minute interval viewership data available. It's extremely expensive. And so I took the compromise road and decided on 15-minute interval viewership data, which I think still gets at the effects I'm looking for. My play-by-play data has nearly 1.4 million seconds of play. And so again, in each of those seconds of play, I observe a real-time outcome probability computed for me. There's large variation in viewership. So the average 15-minute viewership is about 2.7 million individuals, but the standard deviation of that estimate is almost 2.5 million individuals. So there's a large variation in that viewership number. You know, you can have a minimum viewership of 265,000 or as much as 21 million, probably for a finals game. And there's also large variation in aggregate player popularity across games. So if I sum up all the all-star votes of all players playing in a game, the average is 6.7 million. But again, standard deviation is close to 4 million. And you can have again, these are national TV games. So you can have as low as 372,000 all-star votes and as much as 17 million. To give you a little bit of context, LeBron James averaged about 4.5 million all-star votes. So just having LeBron in a game alone is already an order of magnitude higher skill or star power than the minimum game that we observe in this sample. This provides some average TV viewership data as a game evolves. And so what I've done here is I've split the data up into the quintiles of the initial point spread distribution and tracked how the average viewership occurs over the course of an event within each of these bins. And so you can see that viewership during the first half of a game is pretty similar no matter what the point spread is. But as you get closer to the end of a game, games that are supposed to be close tend to take off in viewership, and games that are supposed to be less close tend to decline in viewership. this is basically just the idea that the point spread is a pretty good indicator for how the final outcome of a game on average is going to play out. One thing that was surprising to me, and insights are going to be more than welcome on this, is that the TV viewership trajectory is basically monotonic over the course of the game, right? You have a lot of people tuning in at the end of games, less people tuning in at the beginning of the games. I would have thought it would have been a little bit more noisy, just depending on people's schedules and time zones and things like that. But it appears that, especially for basketball, that the end of the game certainly is more just captivating overall, and people are tuning in more then. This again is starting to build evidence for the assumption that expected thrill is decreasing with time remaining. And so as you get closer to the end of a game, people might be just tuning in because they expect the thrill to be much higher then. I'm going to now provide some summary statistics of the suspense trajectory. So again, calculating suspense based on that visual definition I gave. Here, suspense is defined as the variance in t to t+1 beliefs, which is what you have on the y-axis here. I split it up into the quintiles of the score differential distribution in the data. So, as you can imagine, 0 to 2 point games exhibit much more suspense, especially towards the end of a game, than 3 to 5 point games or 6 to 8 point games, right, as you go down the list here. What's also important here is that suspense on average is quite low for the start of games, but as you sort of increase or go along in a game, you can see here that the average suspense trajectory is basically increasing monotonically. And that, again, more evidence for that assumption that the expected amount of thrill is highest at the end of a game and lowest at the beginning of the game if we're evaluating that at the beginning of the game before any information is provided to us. Surprise has a somewhat similar trajectory. I think this is primarily a function of basketball, the sport of basketball, where you have continuous and smooth scoring. And so you can have lots of suspense and lots of surprise at the end because each, the situation itself can lead to high variance in future outcome probabilities, but every basket that's scored or not scored also leads to big updating in the outcome probability belief. What you do see here is at the beginning of a game, which I think is quite intuitive, if a game jumps out to a really large lead, like a 14+ point lead, you do exhibit more surprise here because in order to provide meaningful swings in that outcome probability at the beginning of a game, you need to have really big leads to do that, right? At the end of a game, a single, like we saw last night, right? If you were watching the Raptors Celtics game, right? One shot can basically, the Raptors probability before their last shot was probably like 0.1% chance to win, and they make this crazy shot, and then it's 100% chance to win. So that's a huge surprise moment right there at the end of a game like that. Okay, so jumping into the first part of the viewership analysis, I have a little bit more than 15 minutes, so I'll try to go along a little bit quickly here. My goal here is to determine if the initial viewership is affected by skill and expected thrill. So again, skill I'm measuring as the total number of fan all-star votes of all players in a game. Expected thrill, because thrill is something that evolves during the course of a game, I need to figure out a way to have a proxy or a definition for the expected amount of thrill that I expect to happen during a game. And the way I'm going to do this is I'm going to use the absolute point spread and provide the extent to which the absolute point spread predicts the cumulative thrill over the course of the game, right? Because the observable metric basically of the logical observable metric of thrill before a game happens is, again, that absolute point spread. How competitive or not competitive do we expect a game to be? There are, of course, other metrics that might predict thrill at the start of the game, but this, I think, is the most logical one for this exercise. So what I do here is a two-stage least square strategy, which I'm not trying to satisfy any of the IV assumptions. I'm only trying to use the variation in absolute point spread as it relates to cumulative thrill, which is this first stage regression, plug in the fitted values from that first stage into a second stage regression that measures the cumulative thrill fitted values from absolute point spread on initial viewership right at t=0 of a game. Okay, so basically two like sort of sub questions: is thrill predictable by absolute point spread? And if so, how much does that predictable thrill affect initial viewership? So a lot going on in this table, so I'll walk you through the important parts. This first column represents the first stage. So what I find here is that the absolute point spread has a negative but insignificant relationship with the actual cumulative thrill that occurs during the course of the game. I should say that I calculate cumulative thrill by summing up all of the instantaneous suspense and surprise that occurs during a game. And then I regress that metric on the absolute point spread for that game. And so the sign is sort of as you would expect. As the absolute point spread increases, you would expect the expected thrill to go down because the game is expected to be less competitive at the end, but there's not very good predictive power here. And so when I actually plug in those fitted values to my second stage, which is in columns 2 through 4, you don't see any significant effect of expected thrill on initial viewership. The second column here is looking at all games, so all 477 games. Then I break it down into regular season games only and playoffs only. What you do see is that, especially in the regular season, that the skill or the aggregate number of all-star votes is highly significant and important for predicting initial viewership. So to interpret this coefficient, a 1% increase in the cumulative skill in a game is leading to a 0.14% increase in initial viewership during the regular season. When you do it for all games, the effect is marginally insignificant, but very close, and the effect size is quite similar. Now I'll jump into the within-game viewership analysis. And so I take a twofold approach to doing this. First, I use an observable parameter of thrill. So the way I do this is I use the score differential in matchup J at time of matchup T, right? So this is a score differential at any given point of the matchup. And then I interact that with the time of the matchup. So I have 12 equally spaced quarter segment indicators. I split up each quarter into 3 4-minute chunks. And then I interact that with the score differential at that time. This is sort of a logical observable measure of thrill because the score differential is important in terms of how close the game is, but the time left in the game is going to determine how that score differential feeds into the potential belief updating of outcome probability, right? What's also really great about this analysis is that I can include game and quarter segment fixed effects. And so I control for anything that's time invariant and known about a game. And I also control for general viewership time trends over the course of the game with these quarter segment fixed effects. The primary assumption I'm making here, which actually it's on my to-do list to test because it's testable, to get a causal estimate, is that the evolution of the score differential is random, conditional on time invariant game-specific characteristics like we know who's playing, we know the trends of how Warriors tend to explode in the third quarter, things like that are known prior to a game and fixed, as well as general within game time trends of how scoring evolves. So again, like the way I'm looking at this is conditional on like what we know the point spread to be and all these other time invariant game characteristics and general scoring trends over the course of games. Each possession is like a dice roll for whether a team is going to score, which I think is, at least in my mind, is feasible, is logical. I'd love to hear if people think that there are important reasons why that assumption might not hold. But because so much gambling in sports, I think this is a reasonable assumption to make in this setting. Okay, so here are the results from the observable empirical analysis. So to walk through this graph, the x-axis is split up into the 12 equally spaced quarter segments. The y-axis in this top graph is the ratings change. Each of these dots represents a coefficient, and you can interpret the coefficient in sort of relative to the omitted category, which is the 0 to 2 point scoring bin in the first segment of the first quarter. And so what you can see here is that there's basically no viewership effect associated with the score during the first half of the game. But as you get into the second half, if the game is sort of out of hand or not very suspenseful, you have tapering off of viewership with this 14+ point category, while you have an escalation of viewership for games that remain quite suspenseful. This bottom pane tells you the distribution of score differential by quarter segment in terms of the percent of game seconds. So you can see here at the end of the game, about 40% of game seconds end with a 14+ point score differential. So these blowouts are a non-negligible component of NBA games. In the beginning of the game, obviously most games are going to start quite close, which is why you have more than 50% of games in terms of game seconds at that 0 to 2 point differential. To put some monetary values on this, what I do is I assign a reasonable cost per 1,000 viewership minutes measure from an advertising standpoint. So I use a number of $25 per 1,000 viewership minutes. If you just look at the difference in the last quarter segment between a 14+ point game and a 0 to 2 point game, assuming that advertising time is about 20% of the time spent watching, you end up with an amount of money that's equivalent to a $50,000 loss if you're, or $50,000 difference between a 0 to 2 point game and a 14+ point game. I think this is a heavy underestimate because it doesn't include all of the indirect effects associated with competitive and suspenseful games. that go with sort of building the brand of a product or having people watch in the beginning of the game in the first place. If you aggregate up all of those differences between this 14+ point trajectory and the 0 to 2 point trajectory over the course of the second half, it amounts to about $130,000 difference in terms of money. What was interesting to me is that we see that there's clearly like a different pattern for this 14+ point trajectory than, basically the remaining 80% of the distribution. So I wanted to split up that last 20% into even more bins. So here is how the tails of the distribution manifest in terms of rating exchange. And you can see it really even fans out even more. And so the extent to which a blowout is happening in the second half has huge impacts on the viewership response. So even a 14 to 18 point game, the difference between that and a 0 to 2 point game is about the same as the difference between that and a 23+ point game, even though the suspense and surprise profiles change between those two different things is completely different, right? If we have a 14+ point game in the last part of the fourth quarter versus a 23+ point game, those are basically both very unsuspenseful and unsurprising situations. Okay, and so finally, I want to jump into the interacted model. So this is the model that's going to rely on the structural parameters of suspense and surprise that I take directly from the definitions of Ellie et al., as well as include the star power element in this viewership data as well. So the goal here is to estimate the within-game viewership responses to suspense, surprise, and star power, accounting for potential interactive effects between them. And so what I'm doing here is I'm measuring viewership for game J at time t in response to suspense in that game at time t, which is XJT, surprise, which is Y sub JT, and then skill or star power, which is S sub JT. You'll notice here that S is now indexed by T. So what I'm actually doing here is I'm using variation in when players are on versus off the court at any given time during a game, because I observe which players are playing. So what I'm basically going to be measuring here with this gamma term is the intensive margin viewership response to star power. So do people basically turn the channel when LeBron goes to the bench or not, right? So that's going to tell me something about that, which the previous estimates that I showed you with the initial viewership decision and the willingness to pay are more extensive margin, like at a game level effect. I allow for there to be interactive effects again between suspense and star power and surprise and star power, and again include game and time of game or quarter segment of game fixed effects here. So this is the final results table that I'll present today. I know there's a lot going on here, but I want to just direct your attention to column 3. So the reason why there's these 1 minute window and 3 minute window is that's the window with which I calculate suspense and surprise. So you have to define a discrete window of time to either have like a backward looking belief updating. In this first set of 3 regressions, it would be a 1 minute of playtime backward looking or forward looking window. The second set of 3 regressions will be the 3 minute forward or backward looking window. What you can see here in columns 1 and 2, you can see that these are the uninteractive models. So this first column basically shows me for a 1% increase in surprise or suspense, what is the percent response in terms of viewership. And so these effects might look pretty small, but remember that you can have as much as 18 times suspense or 14 times surprise for games that feature certain common characteristics, especially towards the end of a game. And so using these estimates, what you find is that an 18 times increase in suspense is about a 7 to 11% viewership increase, while a 14 times increase in surprise is about a 9 to a 13% viewership increase. What's important in the second column and this fifth column is that I control for the raw absolute score differential, because I want to deconfound the idea of a close game with a suspenseful or surprising game, right? But you can have, I think to give like a concrete example of that, you can have a very close game at the beginning of a game, right? The game is just starting, it's 0-0 or 5-5 or something. That's a really close game by definition, but not a very suspenseful one, because the potential updating and beliefs about the outcome probability is very low. There's not going to be much variance there. And so I'm controlling for that effect, but as you can see, the average effect of the score differential going up is a negative response to viewership, right? Which is what you would expect as in this case. In the third column and in the 6 columns, these are the interactive models. So I include these final 2 terms which interact surprise and suspense with the star power metric. You can see that there's not an interactive effect between surprise and suspense, but surprise and all-star votes. But interestingly, there's an interactive effect between suspense and all-star votes, and it's negative. So what does that mean intuitively? That means that as a game becomes more suspenseful, a game featuring more all-star votes or more star power is going to have a lower viewership increase than a game featuring less star power. And I think that's relatively intuitive and actually quite interesting, because it's kind of like the common idea that I'll only tune into a game that sort of doesn't have very many stars if it gets close, right? I want to watch the end of a game if it's really close and suspenseful. But a game featuring LeBron or Steph Curry, even if it's a blowout, potentially I'm more interested in watching that game as long as they're on the court, because there's that star power allure there. And this is just to show you breaking down the superstars that I actually looked at in my willingness to pay analysis. Here are the intensive margin viewership impacts. So the way I do that is I calculate each of their total all-star fan votes, and then I calculate, using the data that I have, the average total votes when they're off the court. And so this tells me sort of what's the margin of adjustment in skill when this player goes on versus off the court. So LeBron, for example, he has 4.6 million all-star fan votes on average between these two seasons. His average total votes when he goes off the court is 3.3 million. So his viewership impact would be, the intensive margin viewership impact would be approximately 2.8%. An interesting one, I think two other interesting ones to point out. Luka here is a very high all-star fan vote number, but doesn't, when he's off the court, there's very little remaining star power based on the profile of Dallas Mavericks games. And so his viewership impact on the intensive margin would be around 7%. On the other hand, you have a player like Steph Curry, who has 3.8 million all-star votes, but when he's off the court, the Warriors still had a lot of star power, right? You had Durant and Thompson, Draymond Green. So he would have a lower viewership impact based on this analysis here. But I think it's really cool that you can see these intensive margin effects on viewership. So I have 4 minutes left, or 3 minutes left, right on time, to just conclude briefly. Where I see this work is that economists are interested in demand for product attributes. The entertainment market is relatively understudied. Maybe this group disagrees with that. I think in much of the commonplace economics literature that I'm familiar with, I think there's a relative under appreciation or under study of work of the entertainment space. It's cool. I think that I have a measurement in comparison of skill versus thrill, and I have an empirical analysis that jointly assesses the two. And finally, it's important, obviously, because consumer attention and demand is essential for targeting and industry profit. It's important for the leagues. It's also important for the TV networks and advertisers themselves. I develop a framework to assess spectator utility in different settings and from different entertainment characteristics. It's I think, a pretty holistic framework that, again, includes these really probably the two of the key elements of viewership, which is skill and thrill. And I find really important and significant effects on willingness to pay and willingness to watch, including that negative interactive effect between star power and suspense. And so just a quick bullet on future work. I think there's a couple, well, besides the counterfactual structure, which I think would be very interesting, one idea for that counterfactual structure is actually to think about what would happen if a game, instead of having a game count for, having one final outcome at the end of a game, you had multiple final outcomes during the course of the game, right? So essentially creating more finality in an event could induce just by construction higher suspense and surprise as that event takes place. And then second, I think, which would be really cool, and actually a project that I more recently thought of, is to assess individuals' value of leisure time using variation in demographic, game, and skill and thrill characteristics, right? So if we have people on the East Coast or the West Coast or people in the UK watching basketball, certainly, that's going to be coming at different times of the day, which is going to reflect people's different schedule variation. So certainly, I don't really want to be watching basketball at 3 a.m., but if I'm in the UK, I may not have a choice. And so we can use variation in skill and thrill, which is pretty exogenous, to say, well, how do people what is their threshold for these things to turn off the TV, right? So if I'm watching in prime time, like around 7 p.m., my threshold is likely much higher than if I'm watching at 11 p.m. and the game is sort of starting to get out of hand. I need to go to sleep because I need to work tomorrow. That might affect my decision there. And so I'll stop there. Again, really appreciate you all having me, and I'm really excited to discuss and take your questions now.
Okay, thank you very much, Scott. Really interesting talk, very comprehensive, very good job market talk. There's been a few questions in the chat, so I'll go through those quickly first off, and then we'll open it up to general questions. So
should I go ahead and stop sharing, or would you like me to keep it on?
Um, uh, it may be that it's good to refer to your slides. One thing you might do is your camera's turned off, so we can't actually see you. So
Oh, okay.
A little blob. I don't know if you're able to.
Okay, let's see if that's. I'm back.
Yep, there we go. You're back. So, okay. So the first question is from Jorge Tovar, and he says the absence, I think, of star players is linear. It looks like you've assumed that is. Does it matter if only one star player is absent, or if there's more than one player missing a game? Does it matter more? Is there any kind of interaction effects, say?
Yeah, that's a really good question. I don't examine the like sort of the additive nature of more stars missing a game, mostly because there's not too many situations where that's happening. You know, most teams have at most 2 like qualifying superstar players in this case. The Warriors were totally the exception, I think, recently, but you probably only have a handful of observations where you had that additive effect. There are cases like that, but I haven't explicitly looked at them. So that's maybe a good thing to look at. Thanks.
Okay, and then Carl Singleton talks about your conceptual framework and asks about the idea of thrill if you're not invested in a game. So, you know, should for an individual the thrill be related to how much time they've invested in watching the game already?
Yeah, that's interesting. So like this sort of idea that there's a path dependency in my response to thrill. I think that's definitely true. I think I don't have an immediate idea off the top of my mind to measure that. My data certainly can't tell me about that because I don't have individual level viewership data. So I don't basically see when a viewership tunes in or when an individual tunes in or out of a game specifically. But certainly in theory, you would expect like someone that's just walking into the fourth quarter doesn't really know how games evolve. So the game's evolutionary path most certainly I think affects my investment into the thrill of the current situation of the game. Yeah.
Okay. And there are no more questions. So at this point, we can open it up to anybody who wants to raise their hand, ask a question. And we have Stefan's hand up. So Stefan.
Hi, Scott. Very interesting stuff. So I have a sort of a point of information really and a more general sort of a philosophical question. So one thing I just didn't quite get. I heard you talking about the viewership data. You said something about you having to choose between 15-minute and 1-minute intervals and in terms of the data. So it sounded to me like you have relatively few observations in terms of viewership, and yet in your viewership regression you say you've got over 1 million observations. So I was unclear how you're explaining 200 odd observation data points with a million observations. So I wanted some sort of, if you could just clarify what's going on there. And sort of my more general sort of philosophical question is, I'm just wondering a little bit to what extent these effects are very large, and I wonder to what extent these are really, this is a function of the nature of the sport. So from a policy point of view, supposing you went to the NBA and they say that, oh gosh, well, based on this research, what we better do is make sure every game has a level of maximum suspense and thrill. Would that, in that world, would you get the same kinds of effects? Would you get these kind of such scale of treatment effects, or would you find that, well, once every game was super thrilling, then actually they're diminishing returns, and so you no longer have these kind of effects? So that's a more general question.
Yeah, no, those are 2 really awesome questions. So let me talk about the data first. So you're exactly right in that the like variation that I'm working with on my like dependent variable side, my viewership is at the 15-minute interval level, and so that amounts to about 10 to 12 observations per game, depending on how long a game is going. The 1.4 million number is basically just to show that I have second of play level for every game outcome probability. So the effect that I'm measuring is like this bunching or this average effect at that 15-minute interval level, but I do have single observations for each second of play for the outcome probability, which is more, I think, more useful in like that summary statistics setting where you see how suspense and surprise are defined and evolve over the course of the game. But the variation I'm using certainly, as you mentioned, is at that 15-minute of game level. And then with respect to your second question, I think it's a really good question. It's something that I've thought about, and I certainly agree that there's definitely diminishing returns to thrill. In the Elliott et al. Paper, their utility functions for suspense and surprise are assumed to be concave, which I think is very reasonable. The extent to which like that elasticity, the trade-off between if all games have 1% more thrill, what would be the like viewership response, right? And how does that elasticity most certainly probably isn't constant, kind of like what you were saying. If all games we know are going to come down to like a 1-point game at the end, why would we watch even up until that 1-point game at the end? So I think there's a balance at play where you want to certainly incentivize parity, because parity on average leads to more suspenseful and thrilling events, but you still want to maintain, I guess, that variance that is so fun and interesting about sports, where even a game that's expected to be close could be not very close or super close. Yeah.
Okay, thanks, Stefan. Any more questions? Folk want to raise their hands? Questions, comments?
You guys are easy compared to my usual audiences.
Well, Stefan's trying to give you a run for his money. Stefan?
Great.
Yeah, no, you deserve a lot of questions, Scott. This is interesting. So, if other people won't ask questions, I will. So one thing, I don't know if you know the paper that I have with Alavi and all, where we looked at English. We had minute-by-minute ratings data. And one thing that was very striking we found that in relation to data is that we had minute-by-minute, and there was a very significant jump every 15 minutes. The fixed effects dummies for 15-minute intervals were very significant. And the reason for that was that people switch channels depending on what's on the other channels. So again, you might want to think about what sort of alternative entertainment variables options were available at these different intervals, because there may be significant effects in the jump, and that might improve your estimates a little bit.
Yeah, no, that's a really good point. I can't remember. I know the Alavi et al. Paper, the 2010 one that looks at the viewership data from the college football games, I think. And I think, yeah, like that paper controls for whether there's like a Monday Night Football game, I think, or other events going on, which I think is super important. I guess, yeah, I'm relying a little bit heavily on assumptions there, which is again about this national TV idea where there's relatively little overlap certainly overlap in basketball. So there's less similar programming on that front, but certainly you can imagine like if there's football on or some other event that can be compelling for the same demographics, that would be a potential confounder for sure.
More questions? Comments? Or we can go back to Stefan again if he wants to.
Well, yeah. Well, we should keep the conversation going, I think. I mean, I suppose one other question is really whether the game fixed effects control for all the seasonal variation, and clearly the point in the season matters. And there may be some systematic effects, the nature of the rivalry, for example, between the teams, and some of that, I guess, a lot of that would be in the fixed effects. But would it all be in the fixed effects? I mean, I'm not sure about that.
I think the extent to which there's like seasonal variation over the course of the season, I think should be accounted for. At least the average effect of those should be accounted for in the game fixed effect. Just because like the game fixed effect is meaning viewership across a game, and if viewership tends to be higher in the winter because people are inside more, then at the end of a season in the spring, then certainly yes. I think the one maybe issue with that is games toward the end of a season can start to take on less meaning. And so basically, like, there may be a correlation between like that lower viewership towards the end of a season with just like lower thrill because at the end of the season there's sort of less at stake, I would say, in that sense. So yeah, certainly I think there's a huge advantage of using the game fixed effects, but of course there's going to be potential situations where that causal stuff breaks down. Yeah.
Would there be scope? I mean, you're thinking about the probability of winning a game. I'm sure I've seen papers where people have looked at these changes and the effect that they have on the postseason, for example. So I don't know if that's something that matters. The likelihood of a team making the playoffs versus not making the playoffs at all.
Yeah, no, that's a really good point. And I think there are papers, like you said, that look at how viewership or how demand responds to like the run up to a playoff push for a team. If a team is sort of already, and I think that's obviously highly correlated with like star power. So teams are going to start resting their players towards the end of the season if they don't have anything to play for at that point. Like the Lakers, that was the case this year. So yeah, I think the end of the season presents some interesting potential effects that we need to think about. In the actual paper, I talk about how one of the breakdowns in the potential exogeneity of star power announcements is that a team might reach a position where they're fixed in terms of their seed for the playoffs, and then the announcement of a player missing the final game is not really exogenous once you know that that team has really nothing to play for. So that's certainly an important caveat to some of the identification in that analysis.
And just go on, Stefan.
Yeah. So another question, though, was again going back, and maybe I've not grasped this correctly. So you can correct me if I'm interpreting this wrongly. But it struck me the test you did at the beginning to see whether the ex ante uncertainty affected the demand for the game seemed to me. In some sense, isn't that implying that some fans are not affected by by the expectation of a very unbalanced game, a game without much suspense, and is perhaps that's being captured by the superstar effects? But isn't that sort of slightly concerning for the paper in the sense that you really should think that, I mean, a very unbalanced game ought to have some effect. I mean, I'm not a big fan of competitive balance as a theory in general, but it's something that you'd expect. There's a very, very unbalanced game should have problems, right?
Yeah, no, so I think the issue is less about the response of viewership to like the absolute point spread and more of the fact that there's not a lot of predictive power in the absolute point spread for the like cumulative thrill metric that I measure, right? So, and I think that's actually kind of interesting because it really points out, again, if you believe the identification or the estimation, that just by looking at the absolute point spread of a game, it's hard to predict the evolution of thrill during a game, right? Because it's not just based on a game being close or not close. It's based on how a game actually progresses. The ebbs and flows of a game, and especially the time remaining in a game. So I think I certainly think that and I've done some analysis that suggests the absolute point spread does matter for at least for tickets, right? Especially when the home team is not favored, the absolute point spread has a really important effect. If that point spread gets larger and the home team is not favored, you find that ticket prices respond and they go down, right? But if the absolute point spread goes up and the home team is favored, people sort of don't respond because they may want to see their team win by a lot. In this case, I think it's just there's not a lot of correlation between the absolute point spread and the cumulative thrill metric as I built it with these definitions. Yeah.
Right.
Any more questions, comments? I'm thinking a bit about your surprise measure, Scott, and essentially, if I interpret that rightly, it's if all of a sudden a team, teams suddenly become very far apart in a match. So one team goes 10 points ahead very suddenly.
Right.
Yes, I mean, I always think back to my mind thinks in terms of football, but that's like a team scoring 2 goals in a minute or something like that. And I guess you're probably taking a very agnostic view about how that comes about. But when you're talking about end of season teams not putting out a full strongest squad, is there an element of of this tanking phenomenon going on where a team just gives up at some point? Or there's even something more sinister going on there. I don't know whether you've got any thought on that.
Yeah, no, it'd be really interesting to sort of look at games that might experience that type of effect. I think, like you said, I'm taking a pretty agnostic approach because all I'm looking at is like the outcome probability. If the 10-point run leads to a big shift in that probability, that's a big surprise. If it's a 10-point run when they're already down by 20, that's not going to change the outcome probability basically at all. So that's not going to be all that surprising. So certainly it depends on the state of the game. But I do think that like one thing that, in other conversations I've had is most people tend to think of surprise in a more macro way than suspense. I think they think like, oh, like that was an upset. Like that game was surprising because this underdog won that game. And certainly like you can generalize the definition of surprise and suspense to be at like t=0 start of game, t=1 end of game. And that's like, that's a big updating in beliefs. If like a team started at a 30% chance to win and end up winning, that's 100%, that would be quite surprising. And so, but like, I guess the thing I sort of implore people at that point is saying, are you surprised in the moment that a team wins? Or probably not, because that team was probably very close to winning already at that last moment. So I think it's more about in the moment, like when a team goes on that 10-point run, right? Or the underdog takes a big lead at the beginning of the game or even at the end of the game, right? But it wasn't a big lead before, then that's like the moment you feel the surprise happening, because that's the biggest updating in the outcome probability.
And correct me if I'm wrong, because I missed it in your talk, but are you assuming that the surprise is essentially symmetric across teams, or are you allowing it to be bigger for the underdog if they go 10 ahead? People tune in because this is interesting versus favorite 10 ahead, or switch off now.
Totally. That's a really good question. So in my paper, I have an analysis that basically looks at underdog margin and regresses that on the viewership. And yeah, what you find is that all else equal, if an underdog took the lead versus a favorite took the lead, and like let's say it was even the same change in outcome probability hypothetically, then yes, people would respond more to the underdog effect than the favorite effect, because that's probably thinking again more about that macro level surprise where the underdog is the underdog in the course of the game specifically, not like in the minute of the game. And so people are really responding to like the idea that, oh, like at a macro level, this team has a better chance to win. And that was surprising because I didn't expect them to win the game as a whole from the start.
Cool, thanks.
Yeah, good questions.
Any final few comments, questions for Scott? In which case, perhaps Scott will let you go and get a big coffee to.
Yeah, that would be great.
Well, thank you very much, Scott, for a really interesting talk. Thank you for the questions. Thank you for taking part in this Roses session. Next week, we have Bernd Frick giving the Roses talk next week, and that will be on gender differences in sensation-seeking behaviour, empirical evidence from extreme sports. And between now and then, should you want to present in a Roses seminar during the autumn, you can submit a paper, or at least a proposal, an abstract and title. I sent an email out with the details. You can find the details for the form on Twitter as well. And if you're struggling to find them, drop me an email. So that's if you do want to participate in the Roses seminars this autumn. So it remains for me to wish you all a good weekend, and thank you again, Scott, for taking part and presenting today.
Thanks for having me. This was great.